Hello, everyone. Welcome to the OpenObservability Talks, the November episode. Or shall I say the Thanksgiving episode, as we're streaming on November 26th. So I am Dotan Horvitz. I'm a developer advocate at Logs.io, who's graciously been sponsoring this great episode. What we do here at OpenObservability Talks is it's a live stream, and also a podcast, and we talk about everything related to open source, observability, and generally DevOps. We have a chat with experts from the industry about these topics, and after that, at the end of the episode, usually some news, industry updates. Specifically today, I'm going to actually also share a very interesting survey that has been done, recently published, about the state of DevOps. So tune in, that should be very, very interesting. If you have something interesting to share, or something that you're an expert on in these topics, do reach out and suggest your topic. You can do that over the website, OpenObservability.io. You can reach out via Twitter at OpenObserve, or directly to me at Horvitz. You can see it also here. Whichever way, if you have something interesting, if you know your stuff, then I'd be more than happy to talk. And with that, let's move on to today's episode. All metrics are wrong, some are useful. That's the title, and for today's episode, I'm very, very glad to host a dear friend, Avishai Ish-Shalom. Avishai is a developer advocate at ScyllaDB. Probably heard the name, the open source NoSQL database. I've known Avishai for a decade now or so, since the days that I was in a young startup trying to set up an OpenStack installation and looking for an expert advice. And Avishai had his own consultancy firm, and he was kind enough to help us through these stages. And since then, he's done so many things. He's been an engineering manager. He's been an engineer in VC and many more things that he'll tell us about. So very, very glad to have Avishai here. And now he's converted to the dark side and is now a developer advocate. So I don't know what happened to him and why, but we'll hear maybe about that as well. So let me add Avishai to the stream. Hey, Avishai.
Hello. What's up?
Great to have you here.
Glad to be here.
Thank you. So maybe you've done so many things. I've known you for a good lot of time, so I don't know where to start even. So maybe you can help us and give us a bit about what you've done and what you've been doing recently at Scylla.
Okay, so I'll start from the beginning. I was originally I studied physics and math. I had nothing to do with IT. I was actually planning to become a physicist, and then as those stories go, in a fluke of destiny, so to speak, I kind of found myself being drawn into the IT industry. I worked as a systems guy. I was in charge of systems for an early mobile company, before the iPhones even. I think it was just around when the iPhone started appearing. And it was very interesting because, relatively speaking, we had a lot of scale back then. And we actually learned a lot, the hard way, just doing stuff. And I think I was very, very lucky to be in that place in that time and to be able to learn all that stuff. And then we were actually one of the first companies in Israel to move to AWS. So I had the dubious pleasure of being on AWS from the early days. It was very different from what it is now. Also, we were one of the first companies to adopt Hadoop in Israel, and all kinds of weird technologies that back in the day no one heard of. So this is basically how I started in IT. And after that, me and another guy from who worked at that company, we opened a consulting firm, Fewbytes. And that was, I think, one of the most amazing times of my career, because as a consultant, you get to work with a lot of different companies. You see a lot of different technologies, a lot of different projects, and your learning is insane, just insane. There's, of course, downsides to it. It's a very intense kind of job, and you don't have ownership, for example, which is also kind of a problem. But from a learning perspective, it was very, very well worth it. So I did this for 6 years, and after that, I did a bunch of other stuff. I worked at Wix as an engineering manager for a while, which is also very interesting and like a very different conversation. It's a very interesting place to be, where there's a company that's growing up and starting to consolidate and become, like a proper, I should say corporation, because it's so big that it has to be a corporation now. I think it's like 3,000 people now. It was 1,700 when I joined. Maybe it's even larger now. So it was a very, again, interesting place and time to be in. And after that, I moved to Aleph VC. Aleph is a venture capital firm here in Israel, which is an investor in a lot of great companies like Lemonade, for example, that IPO'd recently. So that's one of those companies. And that was a very different type of job, but also very, very interesting. And I think from all the places I've been, this is the most, it's a small firm. It's about 20 people, and it's kind of a hatchery for companies. So you get to see everything from the back-end side of how this, of the companies, how companies are formed, how does this magic of a founding group happens. We have founders and the initial people that work with them to start the companies and all that. It's a very interesting, again, different conversation.
Whole new story, yeah. Well, what drove you to the developer advocacy? That's the ScyllaDB.
So a lot of things, actually. So first of all, I've been doing this kind of talks and writing and lecturing, that kind of stuff, for a very long time now. I've always had a passion for this, and aside from that, I've known the people in Scylla, Developer Advocacy specifically, since the days of Fewbytes. I actually helped them with the former project, OSV, which was very innovative, and I always had an eye for them because they were doing a lot of very interesting stuff, and we kind of flirted, every year or two, we'll be like, oh, maybe we should work together at some point, and eventually it happened. Why developer advocacy? Because first of all, I think it's very important, especially in companies like Scylla and also companies like Logs, in companies that build the infrastructure for tomorrow, basically. We have this kind of, I should say, counterbalance in every industry, actually, between the stuff that already works and is solid, and the next generation, which is like different. It's innovative, so it has to be different by definition. So it's kind of disruptive, and there's always this momentum of not going there to the next generation, but you have to, because things do change. So getting this process running and getting people to use it, and when I say use it, I don't mean just on board on the technology, but understand the difference and use it in a different way. That's very interesting, because often what you find out, and this is what I've learned in Fewbytes, that the problem with adopting new technology is that it's not only in installing it, it's in behaving differently, it's in using it differently. It's sometimes you need a different company structure, which is what Devops is all about. So
I think it will relate very nicely also to what we're going to talk today, because many of these notions of observability in general and monitoring, at least modern systems in particular, requires a lot of shifts in the mindset.
Exactly.
So maybe we'll start with the basics. We have, everyone knows logs. That's the basics usually, and then you have the metrics. They're pretty, different. This is quantitative bits of numbers, and these are, verbose and maybe less structured. Can you tell us about how you see the main differences between logs and
Okay, so logs, basically, you could treat them as raw data. It's events about something that happened. And of course, there's a lot of stuff that happens, and you actually make a decision of what to log and what not to log, and you can't log everything. So there's, kind of a gap between, all the millions of events per second that happen in the CPU and the logs that you emit. But still, it's a lot more data than what you have in metrics, for example. So you could think of it as raw data. And from there, you start extracting metrics, so to speak. So a metric could be a count of events, how many events per second you had in a log. That's a metric, throughput of the log. It could also be a count of a business event that happened. How many users hit your server at a certain point of time, how long they took. So again, another metric. So it's basically counting and aggregating things that happened, and events would be the raw data of what you think happened. And if you think of it this way, then metrics are kind of a lossy compression of events, basically. And when I say lossy compression, it's a very important concept because it's very different from lossless compression, which is you've lost data. So it's like an MP3 compression. So you give up some data, and what you gain is basically new data that is a lot smaller. And because it's smaller, it's easier to work with, it's easier to collect, it's easier to process, easier to display, and so on, so on, so on. Of course, there's a downside, just like in MP3, which is you have to decide in advance what you throw away, what you lose. This is what lossy compression means. So that's basically the difference in my eyes.
Yeah, but then I guess it begs the question, when you throw something, you need to decide what's the importance of what you throw, so to throw the less important thing. But then how is it easy to determine what's important for you, especially up front?
So it turns out it's not so easy. So that's really the basic problem with metrics. You have to make a decision up front of what you're interested in and what kind of questions you're going to be able to ask after the fact. And this is something that's being neglected in a lot of metrics setup, because what usually happens is you set up some kind of metrics collector. Might be a library in your code, might be an external collector, doesn't matter. But this collector already comes with a preset, preset metrics. So it's someone else thought about what you might be interested in and has made decisions about what kind of questions you're going to ask. And you've basically taken that and those assumptions, and now you're working with them, and you're kind of stuck with them. And if you actually, think of the process, then you want to start from what questions am I interested in, and not always up front. Sometimes it's a learning process. You start with a certain set of questions and metrics, and then over time you add more metrics to answer more questions that you might have.
I think actually it's an interesting point, because too often I see people taking sort of what comes out of the box, or what's the default or the setup as the given, and they don't even stop and try and map that to the needs of the organization. So they end up with things that don't necessarily reflect what they need in their system. It's a great point. And also I think it's you came from physics world, so you know it better than me, but the measurement problem of having something continuous, and then you need to somehow sample it in intervals, so you get a discrete representation, so to speak, for something that is continuous, which then brings up a question: how do I measure something continuous and reflect it adequately in discrete points, especially since, again, so you get the default out of the box, 60 seconds. Is 60 seconds the right resolution that I need? And what is the right resolution in that case to reflect? So how do you see it? What's the best way to sample in order to reflect a continuous metric?
So if we're going to be accurate here, it's not actually continuous. Computers are discrete. Like if you look at the CPU, it has a frequency of, let's say, 3 gigahertz. So it basically fires 3 billion times a second. That's not continuous. It may appear continuous because it's really, really fast, but it's not continuous. We could, in theory, measure 3 billion points per second, but where are you going to store it? How are you going to transmit it remotely? How are you going to process that kind of data? So yeah, you could think of it as continuous. And then you have, like you said, the resolution problem, and also a lot of other measurement problems that some of which we also encounter in physics. For example, in physics, you have what is known as the uncertainty principle, which basically means that you can't measure something without impacting the measured value. Like, if you want to measure it beyond certain accuracy. So you have the same problem in computers, where if you measure your CPU, that measurement takes CPU. So you have to make some kind of compromises. So the first compromise that we do is we lower resolution, and the default is in many tools 1 point per minute. not because this is a good default, but because it's basically the legacy default. Back in the day, we didn't need more than this, like 20 years ago, for example. It was a good default back then. You didn't have a lot of stuff happening. The rate of, let's say, events could have been hundreds per second. Now it's sometimes 100,000 per second. So it's very different now. So that's one thing that happened. Computers became faster. Second thing that happened is that we have more data, and we have systems that can process more data. So we can actually handle higher resolutions now, whereas before, even if we needed higher resolutions, we had to do this compromise because we had no other choice. Now we do. So if you can have higher resolution, you want to use it. The question is, of course, why? Why would you want to do this? Like, where's the benefit? So if you think of, let's say that you think you have a problem of not enough CPU. Okay, so you look at a graph and you say that your process consumes 70% CPU. Okay, so you think to yourself, okay, I'm not out of CPU, but then the question is like, is this 70%? Is this an average over the time span that you measured? Is it just taking two probing points, and when you hit those points once a minute, then it was 70%? What happened in the middle? Could be that in the middle you had a peak, and you actually hit 100% and you were throttled, meaning that the process became slower, or you didn't get the service that you thought. And in practice, it turns out this happens a lot. So this is one of the reasons why resolution is important. Of course, this specific problem can be fixed by choosing different aggregates. For example, max is a good one for this kind of question. Did I hit a peak? That help you with this. But again, you can't answer all the questions. And also you have other artifacts that result from we call downscaling, basically, shifting to low resolution. So the higher resolution you have, the less, let's say, difference you're going to have between the original process and the metrics. And the second question the second problem that this causes is a latency problem. Latency in the sense of our response to the metrics. Because again, metrics are only useful to answer certain questions and to drive certain actions or certain decisions. So let's say that your system crashed, and now you're trying to fix it, and you make a change. How long is it going to be before you see what that change did? So the best algorithms we have for for detecting anomalies or changes in data require about 3 data points. That's the best algorithms. Realistically speaking, to see a trend, you need probably around 5. So 5, and you get 1 point every 1 minute. That means like 5 minutes minimum before you see that your change actually impacted anything. If you have a metric that has a resolution of 10 seconds or 1 second, you can actually react much faster. And there's actually mathematical proof in control theory, which basically says that the longer the time delay you have for a control system, it might be a human or automated controller, doesn't matter, the faster the controller is, the easier it is to control the thing. And the slower it is, the more problems you're going to have. So that's another reason.
Yeah, I guess this is the trade-off that we all are trying to meet in the real world. Obviously, you would like ideally to have the raw data, but this is the storage size is an issue, with any data.
Yeah.
So
and also the latency.
Yeah, and the latency, as you said, because if I aggregate 5 data points over 60 seconds, that's a lot of time to react, just to discover, detect. So the question is, I guess, how would you say, like, what would be the best practices in how to balance between keeping the data, the raw data, let's say in Elasticsearch or something like that, and then the roll-ups and the downsampling? Any guidelines that you found useful in doing that?
Yeah, so the first question is, can you downscale? Because you can't always downscale, especially if you're already pre-aggregated. There's a concept of whether or not your aggregates are compatible with certain computations. For example, percentile is a good example. You cannot sum percentiles. Okay, so let's say you have percentiles that are in 1 minute resolution. There's no way to move them, to shift them to 10-minute resolution. So you actually have to make this kind of decision up front. So first of all, you have to understand if the aggregates, the metrics that you've chosen are compatible with those kind of downscaling computations. So that's the first problem. Second problem is deciding, what the original measurement would be and how much storage or money, basically, you're willing to expend for it, how important it is. So there's a lot of companies that actually have a tiered approach to this. For example, you might have high resolution and you keep that for a day or a few hours, and then you have low resolution metrics that you keep for longer, maybe a few months even. This has been a common approach in a lot of places like Facebook and Google, and also I'm pretty certain that in Logs.io somewhere you have different tiers for fresh data, and yeah, makes sense. So this is something that's very common in a lot of metrics pipelines, but you also sometimes have to make this decision up front because of this downscaling problem and compatible computations. Alternatively, you could make a different decision. You could decide to give up on accuracy in the measurements and gain compatibility in computations. For example, this is what histograms do. So histogram is a different data structure for distributions, but it is summable, meaning that you can take a histogram of a few servers and sum them up. You can take a histogram of a few time windows and sum them up, and that gives you the ability to downscale and answer certain questions like what is my P99, 99 percentile. The problem with histograms is that to convert from histogram to P99, it doesn't give you an exact value, it gives you an estimate of that value. So trade-offs, this is basically engineering. But the key here is to be...
because obviously the size as well, because histogram is more consuming than a data point.
Yes.
So again, going back to the sizing issue and the limits there.
Yeah, exactly. So a histogram is also bigger. It's a good point that you raised. It's bigger in terms of throughput and in terms of storage and so on. So again, you have to make this trade-off and decide what you want to do. And histogram is more generic, but of course there's the accuracy trade-off. So the first thing that is important here is to be aware that this exists. And then you can make good decisions about how to design this and decide what kind of metrics you want. The second thing is to be aware of your storage and what it's capable of handling. Not all storages support variable resolution, for example. Sometimes you have to do it outside of the storage. And also, if you're not aware of what kind of calculations and aggregations the storage is doing when it's downscaling, you can actually have artifacts, actual things that happen in the metrics that have nothing to do with the original measurement. And Graphite, the original Graphite storage engine, which was called Whisper, actually did this a lot. And people were not aware of this. And I actually had a lot of examples of artifacts where you see something that looks like a problem, but actually this is just Whisper aggregating your data, and you weren't aware of the way that it's aggregating it. So again, you need to be aware of what the storage is doing and how it's doing it. Or you can do the aggregation outside, but then of course you're dependent on the pipeline tools and all of that. So again, trade-offs, and the main thing here is to be aware of this and design it upfront, because this is one of those decisions that it's very hard to do this after the fact. If you don't have the raw data, it's almost impossible to change the aggregations.
I think it's an excellent point, especially since, if you look at distributed systems and in clustered architectures, you also, beyond everything you said, you also need to say, okay, in which granularity in the architecture do I need to see? Do I need to see the individual server or host or node or a cluster or across namespace? Or because not every time, if you didn't do that up front, you won't be able to, as you said, it's not additive, so you won't be able to deduce that and cluster it as a computation lab. So you also need to understand your distributed architecture and then understand in which granularity of the units of architecture you want to operate, no?
That's very true. This is one of the reasons why observability became a thing now, because back in the day, first of all, you didn't have a lot of servers and you didn't have a lot of containers, so this problem wasn't as big. And second is that we actually have a lot more things happening right now. We have systems that have bigger scale, we have systems that are faster. So this kind of problem used to be theoretic for most companies. It was, of course, a problem for larger companies always. But now it's like a commodity problem, so to speak. And you actually have to deal with it somehow, because like you said, especially for percentiles, which are not additive, you either have to measure for all of them upfront, or you have a problem. And the thing is, in regards to your question, like which measurements do you want, the answer would be all of them, right? You always want to know everything, and especially when you're debugging, because you don't always know upfront what you're going to need. So you want everything, but it's of course impossible to have everything. So again, you need to make some kind of compromise. And then, it really depends on your scale. What a lot of people don't realize is that for a certain scale, which a lot of companies are, within the bounds of that scale, you can actually get pretty much everything. It's not that expensive, not anymore anyway, because storage has become cheaper and because network has become cheaper and so on. So people store gigabytes of logs per day, and that's not a problem. And if you have the logs, you can actually derive from the logs pretty much all of the metrics that you want. And the same goes for all other observability infrastructure. It basically works the same way. You basically save a lot of information, and then you basically aggregate it on the fly when you need it. So if you can afford it, you don't have to do this compromise with metrics that is basically lossy compression. Lossy compression is only good if you cannot, alter all data. And if you ask audiophiles, for example, they would tell you that they prefer, uncompressed audio if they can afford it, of course. Yeah. So I think it's a matter of knowing what your budget is, so to speak.
Yeah. You mentioned, I think before, the topic of sort of the artifacts that you get within the metrics if you don't tune it right. Maybe just to help our listeners understand better what kind of distortions you may see, both artificial ones that don't exist in real life or real ones that you may miss out on. Can you give us some examples and maybe some best practices in choosing, because you said, okay, percentiles versus averages and max for that one, maybe some guidance on the aggregations and how to utilize them and choose the best ones?
So let me give a very common example that happens in almost all the metrics and monitoring systems that I've seen. It's called peak erosion. This problem was originally popularized, published, if I remember correctly, by the Zirconis, I think Dr. Heinrich Hartmann. And basically what happens is that on a screen, you have a number of pixels. That number of pixels is limited. A graph has, let's say, 1,000 pixels. So what happens when you have more data points than pixels? That's a kind of problem, right? So you have to somehow downscale again. And what most of the systems do is they average. They take the average of, let's say, you have 100,000 data points and 1,000 pixels. So you average every 100 points to 1 pixel. So the value that you get is the average. If the value that you get is the average, what happens to the peaks? They're gone. So what you see is you see a graph, it looks kind of okay, and then you zoom in, and all of a sudden you see lots of peaks. So every time I see someone look at a monitoring system, a graph, and looking for problems, I'm like, okay, zoom in here. And they zoom in, and all of a sudden they're like, oh, wait, what happened here? Where's this peak coming from? Like, I haven't seen it. And this is a problem that exists in almost all monitoring systems. There are very few systems that, found good graphical solutions for this, like, for example, overlaying 3 lines, the average, the max, and the min on the same point. So there's like different solutions to this, but most of the monitoring systems don't do this. So this is something that I recommend that you go and try almost immediately. You're going to be amazed at what you found. And the second thing is being aware of what you look at, because a lot of time people look at the wrong graphs, the wrong metrics. So another example would be average versus P99. Most of the problems, especially when you're talking about stuff like latency, you don't see them in averages. You actually see them on the high percentiles. So if you're looking for a problem in your database, for example, probably it's a good idea to look at the P99 of latency and not the average. So understanding, again, the relation between the questions you ask and the metrics that you should be looking at, that's very important. So practical advice would be start learning this. Start learning wouldn't even say the mathematics, because you don't have to actually dive into the mathematics of this, but understand the rationale of what aggregates we use and what questions they answer.
And I think what you said, I think the average, I guess, is the most common mistake that I've been seeing. Average by definition, smoothen things, right? By definition, if the search is to see the anomalous behavior, then you would look for something that wouldn't smoothen, but actually flash out the thing. So I think you gave good examples both on the P99 and on the Max that you said before on the latency. These are classic ones that would be definitely useful. We mentioned before the topic of sort of the change that systems have gone through now that we have much more distributed systems, many more components, and so on. So I think that maps in a way to what we hear more and more recently about the high cardinality metrics. And again, we hear more about it, especially with the rise of the microservices and Kubernetes and so on. But could you explain to us what is it for you? What is high cardinality metrics, and why do we hear more about them these days?
So first of all, high cardinality basically means that you have a lot of distinct or different values. Okay, let's say you have a set of data. Let's say you have a group of people and they have names. So how many names are in the group? If you go to a country like Finland, where they apparently have a closed list of names you can choose from, the cardinality is not very high. You don't have a lot of different names in Finland. Whereas if you go to countries where people are free to give whatever names they want, like in Israel, there's a group of common names. For example, Moshe Coin or Avi Coin, I think, is the most common names in Israel. But then you have a very long tail of very, very different names. Maybe some names that exist like once in Israel, only one. I think that Avishai Ish-Shalom is the only one in Israel, as far as I know. So lucky me.
Special.
Yeah, exactly. So this is basically cardinality. How many different values you have in a certain group. And the problem with high cardinality is that from a computational perspective, it's very hard to handle. Basically, if everyone has the same value, you only need to save it once. So it's very cheap, so to speak. And a lot of our systems kind of build on top of this. And they do, again, lossy compression. And they utilize this kind of fact. And they throw away all of the long tail, which usually you don't care about. And that's how you get, small data set from a large data set. However, if you're interested in more functions, usually, like you said before about percentiles, you're interested in the anomalies. You're interested in those things that only happen rarely and are different. So you're actually interested in the long tail. And this is where you get interested in the high cardinality. So a common example would be, let's say that you have a system. It might be distributed, it might not be distributed, doesn't matter. And that system has, let's say, 1 million clients. So a very good example would be Wix. Wix is basically the long tail of the internet. It has millions of websites. I think that, I don't remember the statistics, but I think like over 2% of the websites in the entire internet are on Wix. So it's pretty big in terms of cardinality of websites. And then one of the websites causes a problem in your system. The question is, which one? So it doesn't help you that you have metrics that are per server. You're actually interested in, which of the 200 million websites that you host is the one that's causing the problems. And that might be a website that is, very far on the long tail of the distribution that you have. So you need to make that kind of aggregation. You need to say something like, I want latency broken down by website. So how do you break down to 500 million different parts? That's basically the problem of handling data that has high cardinality. That's very expensive from a computational point of view. And it became a very big problem nowadays because a lot more systems have those kind of problems, but you cannot debug by just attaching to a process and dumping data. Okay, so it used to be that if I had this kind of high cardinality problem, I could just load all my data onto, let's say, my SQL instance or Postgres or whatever, and just crunch it there. And the databases, they always have known how to deal with the high cardinality, as long as the data fits on one machine. Yeah, especially if it's a small machine, on a laptop, for example. So right now, it's no longer an option. So we need, better tools to handle this. And this is how, this problem became very prominent in observability, for example.
So now that it's so common, and I would also argue that the adoption of again, microservices, even as the nature of the architecture that is broken down, and with Kubernetes also created additional dimensions and layers that now you need to cross-reference and then dissect across.
That's a very good point, because in the old days, let's say we had, 100, even 100 servers. It's not very hard to keep 100 different data points, or 100 different time series for each individual server. That's not very expensive, and also you have to remember that the servers used to live a very long time. So a certain time series would last a year, for example. You had that server running for a year. But when you have containers, and every container can live, let's say, 10 seconds, then in a certain day, you could have 10,000 different containers. In a year, you could have millions. So that's like very, very high cardinality now. So even stuff that, it was pretty easy back then because the cardinality was very low. Now, because of the way we run our systems, the cardinality is very high. But you should remember it's basically a decision that we make, because we could have collected data per session, even in the old days. We just chose not to, either because it was too expensive or it wasn't interesting enough. But the bigger the systems become, and the more we compartmentalize them using containers or whatever, the more this becomes important. For every division that you make in the system, you have new dimension, new cardinality. So
Exactly, and also there's, because of on the one hand we create these layers and these encapsulations that you said that each one is now a dimension that you want to query by, and on the other end, as you said, it's very dynamic and things change, and then in a way it also shifts maybe some of the questions that you would like to map to a sequence that is logical. So okay, things went spun up and tore down. The same logical flow carried on across different instances that came up and down. So you need to be able to query much more flexibly, I guess, based on logical tagging that will connect the dots between the different physical, let's say, instances that came up and down through the thread that actually logical thread that came through, right?
Yeah, and it's basically a question of identity, so to speak. If you have a container and that container ran on on one server, and then you shut down that container and you move it with a state, okay, but you move it to a different server. Is it still the same container? That's a very good, interesting question, right? Because there are things that are different. It's running on a different machine that might have different performance characteristics. Maybe it has noisy neighbors. Maybe the CPU is different. The clock is definitely different. We've also had this problem with the virtual machine and so on. And you can even ask this question about threads, for example, or containers that move between CPU cores. One CPU core is more loaded than the other one. So it's a question of what do you attach an identity to? If a transaction moved between one container to another, is it still the same container? That depends on it's a decision that you have to make. If you have one transaction even, and that transaction moved between servers, is it still the same transaction? It's a decision that you make about the logic of your system. And so again, it goes back to deciding what the boundaries within your systems are, and you give each of those boundaries like a name. This is like the name of the dimension and an identity of the specific subsystem within that boundary. So you could subdivide the system however you want, but there's some subdivisions are more natural than others, maybe related to resources or services like microservices and so on, so on, so on.
Yeah, makes sense. So if you look at the modern, computing systems and architectures, all these shifts in needs and in the concerns, can you give us some, from your experience, what are the design principles that you would recommend following in these new domains when setting up the monitoring?
So when you think about monitoring and you think about the design of monitoring, you always start from the function of monitoring. And the function of monitoring is to say, this system is working or it's not working, and if it's not working, what is not working, or at least help you understand this. So if you think about it this way, when is the time that you need monitoring the most? When you have a problem, right? So it's advisable that if you have a problem, monitoring doesn't die with it, or at least not being impacted as much by the problem. So the first design principle of monitoring would be to separate monitoring and data metrics pipeline, if you can, of course, as much as you can from the primary system. You don't want it coupled in any way. And it's amazing how many times you see systems, even for very prominent companies, that break exactly that on that point. Yeah, because
Okay, talking about the AWS
yeah,
right, with the US East 1 region, that their actual health dashboard, they stated you can't rely on what they state because the dashboard itself fell apart.
Yeah, so in a complex system, it's very hard to have something that's completely separate. So I understand how this kind of thing is happening. But as much as you can, you prefer to have this kind of separation. So for me, for example, if I'm unable financially or because it doesn't make sense for me as someone who built a system, I would prefer to have an external vendor for monitoring. Why? Because it takes a very large part of the monitoring stack and basically puts it somewhere else on a different type of system that's independent from my primary system. Then I can rely on the probability of both, let's say, logs.io and Wix crashing at the same time is not very high. Okay, with the notable point that everyone today is on US East 1. But if we kind of ignore that for a second, then you get the point. But it also goes down to the basics of how you collect metrics and how you aggregate them and so on. If you have metric collectors on the same machine, this is when we do design in SRE, for example, we call this shared fate. You have failure domains that share the fate that all the components within share the fate. So, for example, if the server dies, all the components from that server dies. And it might be okay, might not be okay. For a metrics collector for that server, that actually makes a lot of sense because there's no more metrics to give, so who cares? But for other places, you don't want to be mixing failure domains. You don't want to have this kind of coupling. So this is the kind of diagrams that we draw for systems, and then we decide how we split the metrics or telemetry pipeline from the primary system. And often in companies, for example, that have Kafka, it's not uncommon to see that they stream the metrics and the logs and the observability data on the same Kafka where all the primary data is being transferred on. So if you have a problem with Kafka or an overload caused by your system, first thing that's going to go is monitoring. How are you going to debug? So that's one very important design principle. Second thing is always start from the top, from the user experience. Like we mentioned before, you start from the questions you might be interested in. So the most important question, of course, is, are my customers getting satisfactory service? So you're actually very interested in the business metrics, and this is where you want to start from. Everything else comes much, much later. The stuff that comes by default, for example, like CPU usage and memory and all that kind of stuff, resource metrics, is actually not that useful most of the time. Why do we have it? Because it's default, it's easy. So that's why most people collect it, not because it's important, because it's easy. It's already there, so to speak. So you start from the questions. You kind of map basic questions that you have about the system, and you continue from there. And that's basically how you build a system. And of course, if you can have the raw data, then as a design principle, always prefer to have the raw data if possible. And then you start making the trade-offs that you need to do. So one of the trade-offs that we didn't mention before is sampling. Because again, if we think about metrics as loss of compression, there's a number of stuff that you can lose. Okay, so some of the stuff might be using sophisticated metrics like percentiles and so on, but other stuff can just be relying on having a lot of data across a certain dimension, and then you can drop statistically some data that's basically sampling and rely on the statistical nature of this data. So basically making those decisions and designing your metrics, that's the important part, because you can actually make better decisions by understanding like what you're going to lose and what kind of stuff you want to lose. So I hope that answers the question.
No, you raised good points, and I think again taking these points and trying to translate them to the practicality, because oftentimes it's not so trivial, I guess, to know upfront what you would need and what kind of data and what will be the usage. So I'm wondering, you realize many things as you go along, and then you realize, hey, I need this and that type of visibility. But how, I guess, what would you say you need to know of our data upfront in order to have proper metric planning? Because you mentioned before that some things are not reversible because you don't have the raw data.
Yeah.
Can you give us guidelines maybe to what you do need to know, or try to clarify as much as possible upfront?
Yeah, so the first obvious guideline would be as flexible as you can be. So if you don't have to make those kind of decisions up front, don't. So usually this means saving logs if you can, and it's affordable, or using some other kind of observability method, where you can answer a very large variety of questions ad hoc without having to think about the questions before. So that's, if you can do this, do so. Be as flexible as possible. That's the first practical advice that I would give anyone off the top of my head. And the second one is, again, start from the user, start from the business metrics. This is like something that's obvious that you're going to have to answer. So without knowing anything else, you have to know this. So you always start from measuring and monitoring the business from the user point of view. And only then, after you cover the basics, so to speak, then you start doing everything else. And then you have a number of, let's say, I don't want to call it best practices because I hate the word, like the concept of best practices. There's let's say, appropriate practices, so to speak.
Takeaways.
Yeah, exactly. You can even call it common knowledge, for example. But there's let's call it playbook. There's a playbook in the industry of stuff that makes sense to do in certain situations. For example, if you have something that has a latency, let's say like a user transaction or the response time of database, ScyllaDB, for example, which is, by the way, very low because ScyllaDB is awesome. But let's say you have this, you always need to have the throughput metrics and the error metrics with it, because latency by itself doesn't tell you much. Okay, let's say you have P99 of latency, but over that time window, you had 50 transactions. You can't actually compute P99 from 50 points, right? So the metric is obviously broken. So having those, let's say, bundles of related metrics is very important. And there's a number of playbooks in the industry, or common knowledge, about what metrics should go together and should be displayed together and collected together, for example. So you can actually map those pretty easily. It's not very hard to do. And then you can apply this in your systems. So that's another very practical advice that I give people. The other one would be know your systems. What do I mean by know your systems? After you have selected a certain vendor or system, doesn't matter, you need to understand how it works. How they crunch the numbers, what kind of artifacts you can expect, how the graphics behave, do they have this problem with peak erosion, what other problems they have, what are they not displaying, and so on, so on, so on. And it's important to remember that even if you find a problem, so to speak, in your vendor or system, doesn't mean that you have to change it, because it's engineering, everything has a trade-off. Everyone is going to have a certain problem, might be a different problem. You need to see what problems are okay for you and what problems are not. So you need to understand the system that you're working in and understand what problems it has. Let's say it's not even a problem, it's behaviors, and learn to live with them, so to speak, adapt to them. That I think would be a better term. So I think those would be the basic practical advices I would give anyone who's starting to build a monitoring pipeline or telemetry pipeline.
Good, yeah, great point. Just a note to our listeners on the live stream, we're approaching the end of the chat with Avishai. If you have any questions, feel free to type them down on Twitch or on YouTube Live, wherever you you're watching, and we'll definitely be glad to ask them to and discuss them with Avishai. I guess maybe the last point you mentioned before, graphite and its anomalies, or tweaks in behavior and things like that. Did you see any impact on the tooling and methodologies following this modern computing systems and this shift that we talked about before?
Yeah.
Has that impacted as far as you see, like graphite, and StatsD for the collection and things like that? Was standard in the industry. You're talking about playbooks. That was an unwritten playbook, and I at least saw a shift from that. For example, the rise of Prometheus and things like that. I'm actually wondering, what have you seen with the tooling and methodologies because of that shift that you mentioned in modern systems?
So that's a very good question. So you have to remember that graphite, despite all of its problems, it had a lot of problems, was actually a very big mind shift in the industry. Before graphite, almost no one collected metrics or displayed it, and the tools we had were horrible. They didn't allow you to do any kind of ad hoc processing. For example, there was RLD tools and Cacti. I don't know if it's a very old system. We use it for routers and stuff. And it didn't allow you to do any kind of post-processing. You couldn't even, apply simple functions like moving average, for example, smoothing. So Graphite was the first tool that actually introduced this concept of post-processing and gave a simple protocol for applications to send their own metrics. This was actually pretty early before Graphite. And later came StatsD and improved this situation by actually commoditizing, let's say, local aggregation or cluster aggregation into systems and cheap metrics, because this StatsD was built for metrics at scale, and it made a lot of assumptions about how metrics are being collected that were very that made sense for certain systems. The problem with StatsD was that everyone took StatsD and started using it without thinking about whether it was designed for the scale. And this caused a lot of problems, because a lot of the assumptions that StatsD made were either only correct in the original context or completely incorrect. And I could give you a few examples. For example, it used UDP. UDP makes a lot of sense if you're trying to protect against overload, because basically packets would be just dropped. But it doesn't make a lot of sense if you're trying to have accurate measurements. Because, for example, the original StatsD was written in Node.js, and basically it aggregated once every 10 seconds. And while it was aggregating, it didn't do any metric collection. It didn't accept any packets. So every 10 seconds, you had correlated loss of many UDP packets. So, of course, that's going to impact the accuracy of the metrics. So it might have made sense in the original context, but not necessarily in other people's context. And also, it made assumptions about the resolution and aggregation, and it made sense for high traffic, not necessarily for low traffic. And then there's the protocols. The Graphite protocols and StatsD protocols were very, very specialized for metrics, and they tried to be very cheap, but they didn't allow, for example, high dimensionality. They didn't support this very well, or high cardinality, that kind of stuff. So we actually saw this shift in the industry for better protocols, and actually we had a lot of attempts, a lot of failed attempts, I should say, of moving to better protocols that are more appropriate for what we need right now. I think there was something called Metrics V2, if I remember correctly, that tried to be kind of a standard for metrics, and failed horribly, never became standard. So one of the problems is that the adoption in the industry is kind of evolutionary. It happens, organically, so it's not really designed in any way. So not necessarily the best tools wins, so to speak. So those tools improve the situation a lot, but they also introduced a lot of other problems, because it's basically a learning process, and along the way we learned that some of the stuff that we were doing doesn't make sense. So nowadays it's very exciting to see all this activity around monitoring and observability, where we rethink a lot of the concept and we correct a lot of the errors of our youth, so to speak.
Yeah, and generating new ones. Actually, we have from the audience and from one of our listeners. As someone that worked around distributed systems for years, and now especially in the database realm, what metrics are important to VMs acting as data storage?
Oh, VMs acting as data storage. That's a good one. So first of all, the obvious question would be, why are you using VMs as data storage? Like especially in the cloud today, like the data storage is hosted by Amazon. Presumably they use VMs, but it's their problem. But unfortunately, I'm working in a company where this thing actually happens. Like a lot of people do run ScyllaDB on virtual machines in the cloud. So what metrics are important for VM? That's interesting because we're not actually that interested in the machine metrics, so to speak. We're more interested in the internal metrics of the database itself, because the real question is up to the point where you start debugging the operating system, because you decide this is what the problem is. Like, what changes in the behavior of the database itself, if that makes sense, because of the external environment. So let's say that the disk starts responding more slowly. Yes, of course, the operating system might discover this, but if it's a good database, the database is going to discover this first, because it's actually being impacted by this. The problem is that in most of the databases, because of the generation in which they were written, you don't actually have those kind of metrics in a lot of them. In ScyllaDB, we actually do. ScyllaDB is like kind of a mini operating system, so to speak, sister framework, if you've heard of this. So it actually outputs a lot of those metrics, like how many pending I/O you have, and what is the latency of the underlying I/O subsystem, and so on, so on, so on. So it turns out that you don't actually care a lot about the OS metrics until you start debugging the OS layer, the operating system layer, and then you have a lot of very sophisticated tools nowadays, like eBPF and so on. So that's the real answer is it's complicated. It's a very long conversation, but one of the most important metrics that almost no one bothers to look at is time, especially in distributed databases. Time across VMs can be very weird. It can go back. It can be different between machines. It can jump ahead in time, and so on. So one of the things that you actually want to monitor, and most people don't, is time.
Yeah, that's a good point. And anyway, I think one point that is I can relate in the question was that the more layers we have in between the bare metal operating system, the host, guest, virtual machine, and so on, it again goes back to the dimensionality, and say we have more accesses in which we may want to query. So we want to query the application itself, like the database as a whole. Maybe you want to query the individual nodes of the cluster, assuming a cluster database. Then you want to correlate sometimes between the database and the instance in which it runs, or maybe even go down to the metal. So it creates more questions that we potentially may want to investigate to get to the root cause. So I guess in that respect, it's complicated our lives in that respect.
Yes, and what you do is you make decisions about what you don't want to debug. Basically, anything that's opaque and you can't look into it, we call it a black box. This is like half of operations is the art of dealing with black boxes. So EC2, for example, relating to the question before, is a black box. Like at a certain point, you say, okay, this is Amazon's problem. I don't know how to debug why KVM on this machine is behaving in this way. So I'm going to just shut it down and move to a different VM.
And that's or even going into a serverless where you get much less visibility.
Exactly. So you accept that there's a certain layer that is a black box.
Yeah, I agree. Well, it's a fascinating discussion. It's a shame that we need to stop it on the hour of Avishai, but it was really great having you on the podcast, and thank you very much for sharing your knowledge. And I can definitely think any more questions that I'd be glad to ask you, maybe even in a separate episode. So thank you very much.
Bye. Thank you.
Thank you. That was a great talk, and with that, I would like to move on to our next topic. And today, before going to the general news, I wanted to share with you a bit about the Devops Pulse survey. That's actually a very interesting survey that has been published very recently around the state of DevOps. And I just would like to share it with you for a few tidbits, and then maybe share with you the link so that you can explore that further. Let me just share it for those that are on the live stream seeing that, but I will also share the questions for those who are on the audio only. So the survey, you can find it, by the way, at logs.io/DevOps Pulse 2020. That's the survey. It covers a variety of DevOps related topics. Each year a different spotlight. This year's spotlight was around the cloud native technology. So very interesting. We had around over 1,000 engineers answering this survey, so quite exciting. Lots of information here, but maybe just a few bits that might be interesting for us. Obviously around cloud. So we mentioned AWS's outage yesterday at their largest and most used region, US East 1, but impacted many of the companies in the industry, like whatever Anchor and Glassdoor and Flickr and others. But nonetheless, the fact shows AWS still reigns the public cloud. Over 66% or 2/3 of the companies use AWS as their vendor of choice for cloud. Also interesting, comparing last year's with this year's, is that Google Cloud has been catching up with Azure for the second place. So interesting. Also, in general, very interesting to see the percentage of users that now use public cloud, and you can see that. I guess you can see that over 50%, maybe even 50 something percent, are having more than half of their infrastructure already on the cloud. 42% have over 75% in the cloud, which is more than 8% increase than last year's survey. So very interesting. Another aspect around the containerization, so not just public cloud, but generally speaking, switching to cloud native, let's call it, or containerized. Again, we see the trend increasing. We have over 50% running their workloads on containers. So definitely we see that trend going further. Again, I won't go over all of that. Maybe something interesting about the challenges that relates to observability is, again, Kubernetes is very popular. We hear so much about it, but it is definitely the number one difficulty that people encounter when running Kubernetes in production. So, security is an issue, networking is an issue, a lot of issues. But the number one is monitoring and troubleshooting. So we can see that as a very common pattern, but we can see problems all around. So again, everyone talks Kubernetes. Some even refer to Kubernetes as maybe a given and old news, but it's definitely not all old news. And we can see problems across the board, people still struggling to have Kubernetes in production, in issues with security and networking and cluster management, and as I said, monitoring and troubleshooting. So definitely Kubernetes is still in the works in terms of getting it right in production. Specifically in observability, again, lots of information here, but one that I found interesting is around the use of the different telemetry data. We're talking about observability being logs, metrics, traces, and so on. I think one of the interesting things was to see that as obviously as logs and metrics being very prominent, we see increase in the use of traces, and also in terms of tooling. When you talk about which tools you're using for your observability, we see distributed tracing as at 26%, and that's massive. If you compare to last year's, it was less than 10%, and this year we see 26%. That's a major increase, like a 33% increase. So again, distributed tracing picking up very strongly with the observability realm. Also, in terms of maybe a last point that I may mention around the distributed tracing is, again, most of them, as I said, are still not using tracing, but the ones that do, definitely we see Jaeger as the leading one in the answers, almost 13% from all across. So that's apparently the leading tracing tool. And there's still sprawl. You still see many using quite a bit of tools, which is something that is still a challenge, I guess, across the board. So again, there's no time to go beyond that, but definitely I wanted to get you intrigued. So you can go to logs.io/Devops Pulse 2020 and feel free to explore yourself and see some more. And with that, I would like to maybe share also a few of the breaking news from the industry. The first one that I wanted to share that relates very closely to the discussion earlier with Avishai is about OpenMetrics project. OpenMetrics project has been announced really now as being a stable release. And OpenMetrics is essentially an open source or an open protocol that is meant for the cloud native realm, essentially for a met-require protocol based on the Prometheus exposition format. And it's targeted to standardizing under the IETF. I think the RFC is already in the works. So it's very interesting again because, as also mentioned in the earlier discussion, has been attempts to try and standardize on this protocol and how to send metrics. And I think this is a very prominent attempt that is also based on well-established experience by Prometheus open source project. It's been in the CNCF sandbox for the past 2 years, and the last this week's SIG observability, the special interest group discussion of the CNCF. We've been reviewing it to help the chair decide if OpenMetrics should be promoted to the incubation stage. So definitely it progresses also on the CNCF. And it would be interesting to see how it will play out alongside OpenTelemetry, which is again also under the CNCF umbrella, and we've been discussing OpenTelemetry also in previous episodes. So that's one interesting bit. The other interesting bit that I wanted to share is around the acquisition of Instana by IBM. Again, Instana is very high-profile startup, a 4-year-old startup. Is being around focusing on specifically the microservices and the cloud-native domains. And it's very interesting to see IBM taking this, acquisition as part of its. I guess it maps very nicely to the transition of IBM IBM is trying to do to hybrid cloud to open source. With the acquisition of Red Hat and adopting OpenShift to the stack, and Red Hat team, by the way, was heavily involved in also in Jaeger open source project with the integration to OpenShift. So it's going to be very interesting to see the synergy there, as well as the synergy with IBM's existing cloud app management that they have, which is also a type of APM. So interesting to see that. Another very interesting open source that has been released very recently is Grafana Tempo by Grafana Labs. It's an open source scalable distributed tracing backend, and I guess the main thing that they try to push here is to try and balance the trade-off, wanting 100% sampling, but not wanting to manage the Elasticsearch and the Cassandra cluster. So they released this open source to try and tackle that. They had the first community call a few weeks ago, this on November 12, a very interesting call. And it's very interesting. Again, first of all, 100% sampling. What's it begs the questions like what's the performance of the ingest, and how does it handle high volume of transactions and so forth. So it would be very, very interesting to follow up on that. Also, seems to be an indexless store, something similar to Thanos and Loki that we've been discussing in previous calls. So writing to cloud storage backend, AWS S3 or Google, or looking into Azure Blob. So this means you can't do open-ended searches usually, but if you know the specific time frame, then you can, the trace ID, then you can find it quickly. So it would be interesting to see how, as an indexless store, how they're going to balance between the open and also cater for the open-ended searches efficiently. And the last bit that I wanted to share is about a new Kubernetes open source distro by Mirantis that's called the K0S, following the K8S and K3S. Now I have KOS, and that's so presumably the smallest, simplest Kubernetes distribution. That's the mission statement. Here's the blog post. I will also post it together with the podcast. It's created by the team behind the Lens, the Kubernetes IDE project. And again, it aims to reduce the complexity of installing, running Kubernetes, being simple, one single binary with no host operating system dependencies, very ultralight, and requiring minimal resources. So that's something very interesting to look at. So I think we're about to run out of time. So with that, I would like to thank you very much for joining me on this on this episode. And if you're celebrating Thanksgiving, then happy Thanksgiving. Obviously, beyond the live stream here at YouTube and Twitch, we also have the podcast available then on demand on the whichever application you have favorite podcast application. I would like to thank again also Avishai Ish-Shalom for sharing with us all his insights about metrics and challenging us to do better on the metric side on our side. Definitely some action points for me to take further. You can find all the episodes at the website openobservability.io, and follow us on Twitter at OpenObserve for updates on the upcoming episodes. And feel free to share comments, suggestions, and we're more than happy to get new ideas and new talks. So if you have something interesting that you'd like to share and to talk on the podcast, do reach out and propose your talk on the Twitter or on the website, or whichever way works for you. And get involved. We want more people from the community involved there, definitely. Thank you for listening. I've been Dotan Horvitz, and looking forward to seeing you again on next month's episode. Thank you very much.